twofold. One is to build an architecture that we can call grand unified, where the notion of a traditionally unified cognitive architecture brought together the high-level cognitive aspects. But here we want to bring in not only that, but also perception, motor, affective, and so on, in a uniform fashion with the traditional cognitive aspects of the architecture. Functional elegance means that you want a broad diversity of intelligent behaviors, but from a small set of core mechanisms. The analogy is to something like a cognitive Newton's laws, where you want a small set of general mechanism through whose interactions yields the diversity of intelligent behavior. And then sufficiently efficient is essentially just being efficient enough to be able to work in real time on the kinds of applications that you care about. Now, the goal here is to build an architecture that supports things like intelligent virtual humans, robots, agents, and so on, that are cognitive, interactive with both social and physical environments, and adaptive to their interactions and experiences. So just as a quick, the approach we're taking is both hybrid and mixed. So we're starting with both discrete and continuous representations, and the combination of symbolic and probabilistic. It's not different representations, though. It's all one that is mixed and hybrid. So just a quick example. This work is going on at the Institute for Creative Technologies at the University of Southern California. These are the kinds of virtual humans that are being developed there for educational purposes. These were tour guides at the Boston Museum of Science. This is an entertainment Old West saloon, and several military applications that involve counseling or negotiation or other things like that. So theory of mind in Sigma. Theory of mind basically models the minds of others. What is my model of your model of me, for example? All of those kinds of things. To understand complex multi-agent situations and to participate in social interactions of various sorts. Now, the approach we're taking is based on the PsychSim approach, based on the work of Marcella and Pinedeth, which is two major components if we don't focus on belief updating, which is not represented in this paper. One is decision theoretic problem solving based on POM-DPs, and the other is recursive agent modeling. And so what we're going to try to do is take those concepts, understand how they map onto the Sigma architecture as we've developed it, and then see what we learn from that attempt. So the questions we're trying to answer in this particular piece of work is, can Sigma elegantly be extended to comparable theory of mind, not by adding a module onto the system, but by making use of the mechanisms that are already there? What are the benefits for theory of mind? Do we go beyond what's been shown in theory of mind so far? And what new phenomena emerge from this combination? The results reported here include an extension of Sigma to be a multi-agent architecture, and the implementation of single-shot two-player games, one aspect of theory of mind. And we've done both simultaneous games where the two are deciding at the same time, as well as sequential games. Now, I'm not going to talk at all about multi-agent Sigma, given the time, and I'm going to very briefly cover simultaneous, and I'll focus a little bit more on sequential moves, which to some extent is a generalization of the simultaneous move version. So, first we'll start with a very brief introduction to Sigma. Sigma is constructed in layers. Stuart Shapiro talked about a layered approach. This is a layered approach as well, but somewhat different. We've got an analogy to computer systems here, where you have hardware, microcode, computer architecture, programs and services, classical computer systems hierarchy. When we talk about a cognitive system with Sigma, we're talking about a hierarchy as well. We don't care about the bottom layer here. The cognitive architecture typically maps onto the computer architecture in analogy with the computer system. And on top of that, we have knowledge and skills. What's somewhat different about Sigma is this well-developed layer below it, which is a graphical architecture, which roughly maps onto microcode or firmware architecture in a computer system. So I'm going to talk about two layers here, one the graphical architecture and the other the cognitive architecture. So the graphical architecture is based on graphical models, things like Bayesian networks, factor graphs, Markov random fields. Those are all examples of graphical models. And piecewise linear functions, which are the core of what allows us to provide hybrid mixed representations. We have a cycle at this architectural level of solving graphs and then modifying them. And we just go round and round that loop over and over again to behave in the system. On top of that, we build the cognitive architecture, which is based on predicates, which form essentially the basis for working memory. and conditionals, which are a deep intertwining of concepts from rule-based systems and from probabilistic networks. And those form the basis for long-term memory. The cycle here, we have basically perceptual transduction, action transduction, and then between those we have memory access, decisions, and learning. What's key is that memory access maps down to graph solution, and decisions and learning map down to graph modification. So this layer is built essentially on top of this layer and reduces to it. So in particular, the graphical models we use here are factor graphs with the summary product algorithm for processing, also known as loopy belief propagation in probabilistic reasoning. And I say up here, the key idea are conditionals, this deep blending of rules and probabilistic networks. Okay, so one way of looking at sigma, this is what it consists of. At a slightly higher level, we can talk about 3 layers of control that happen in sigma. And this is in fact modeled on the SOAR architecture, but with the inner loop being the graphical architecture in sigma rather than rules in sigma. So again, there's a layered notion here, much like what we saw this morning, but it's a different set of layers. The lowest layer, or the inner layer, is a reactive layer. It's essentially one parallel graphical cognitive cycle. You solve the graph once, you modify the graph. Or you access memory, you make decisions, and you learn. Okay? That's one reactive parallel retrieval of information about what to do next. So conceptually, it looks sort of like this. That acts as the inner loop then for a deliberative layer, which involves serial selection and application of operators, where at each step you do this cognitive cycle to decide what operators to perform and, for example, how to apply those operators. So that's standard deliberative behavior. Outside of that, or on top of that, is the reflective layer, where deliberation is the inner loop. But here we get recursive impasse-driven generation of meta levels when, for example, you don't have the knowledge about how to choose what operator, you get a tie impasse. If you don't know how to apply an operator, you get a no-change impasse. If you're familiar with SOAR, these should be very familiar concepts. This leads to reflection and generation of meta levels where you can step back and work on problems in your own behavior rather than just problems in the external world. So this is the inner loop of that, is the inner loop of that. The layers differ in timescales. This is fast, parallel. This is much slower. They differ in serial versus parallel. Serial, these are parallel. And controlled versus uncontrolled, can use knowledge to affect what happens in terms of the processing at that layer. Okay, and we're going to return to this kind of structure when we get to theory of mind. Okay. So here's the simplest form that I'm going to talk about a theory of mind. Single shot. So we're not going to do multiple instances of it, so we're not going to worry about learning yet. 2-player games, but they both choose their action at the same time. So for example, Prisoner's Dilemma. They're both symmetric and asymmetric games. This is a symmetric game where the payoffs for the 2 players are the same. Now, the socially preferred outcome here is, in some sense, the best outcome. If you chose this one, that would be best for both players. Unfortunately, you often can't get there. The Nash equilibrium is a point where neither player can unilaterally increase their payoff by altering their own choice. So that's this one. The key result, and the only thing I'm going to talk about in simultaneous move, is that sigma was finding the best Nash equilibrium in one memory access or graph solution. So for example, in Prisoner's Dilemma, it found this, and in Stag Hunt, an asymmetric, a different game, it's finding this one, which is the best Nash equilibrium. A linear combination of alternatives was used here, which means that it won't always find the Nash equilibrium here, but that's a restriction that's loosened up in the sequential work that I'm going to talk about next. Okay, so without showing the details of how this happens, this is just a basic result that this kind of thing kind of falls out of the graphical structures and processing that's going on in sigma. If we look at sequential games, here we alternate moves. There are different kinds of games. The one I'm going to focus on is the Ultimatum Game. We're going to use a decision theoretic approach, like with PsychSim, with a softmax combination. So instead of linearly combining the alternatives, what we do is we take the probabilities for the other person's move, we exponentially transform those. We take the utilities of the opponent's moves, we exponentially transform them, and use those as the probabilities for their moves, like a Boltzmann distribution, and do that in combination to get the expected value for moves. So that's what we're doing here. It turns out there may be many Nash equilibria here, so we're looking for a stronger concept of subgame perfection, where essentially you use an equilibrium strategy over any subgame. So at each step, you want to be choosing kind of the appropriate move that way. The key result here is that these games are solvable in Sigma in two distinct modes. One of them that can be called automatic, or you can call reactive. If you're familiar with Kahneman's terminology, it would be system 1. And the other is a controlled or deliberate, actually reflective, or system 2 kind of approach. Both modes are well documented in human processing for many kinds of things, but they're not previously found in theory of mind work. So this demonstrates those both coming out of the structure in Sigma. Here's the ultimatum game very briefly. Agent A starts out with a fixed amount of money, decides how much it wants to offer to B, and then B decides whether to accept or not. If B accepts, each gets the corresponding amount of money. B gets what it accepted, A gets the rest of it. If B rejects, they both get 0. There's also then a utility function over the money. Each agent can have their own. In this case, we'll use the same utility function for both. So here's the automatic or reactive approach. It's all within memory. It's a single graph cycle, automatic or reactive. What we have is a trellis factor graph with one stage per move. And we're focusing on the backwards messages from the wards back to the decisions about what action to perform. Essentially, B is choosing based on the reward it gets for the money for the offer made in its choice, and A is choosing based on the expected value over B's choices of the reward that A gets for its money times the probability for B, where this is the exponential transform of that. Now, the interesting thing in the Sigma implementation is you don't see any of these calculations showing up. That all happens as a consequence of the semantics of factor graphs and the way it's implemented by the summary product algorithm. So what we see are things that look like fairly conventional rules. This defining the reward function, this defining the transition function for B, this defines the transition function for A. The only thing that's done kind of specially, and I'll mention that again later, is the exponentiation. But otherwise, what we have are these fairly straightforward things which end up making this calculation and choosing appropriately. Okay. So that's the reactive approach. One decision, you essentially solve the graph defined by those conditionals, and you get out an answer for what A should do and for what B should do. The other approach is a controlled, deliberate, reflective system 2 approach. That, again, will look a lot like what you might see in SOAR in problem-solving the 8 puzzle. But it's doing, again, decision-theoretic problem-solving here. We start with the problem of deciding which offer to make. You don't know, so you get a tie impasse. You try to evaluate alternatives. You don't know how to evaluate them, so you get a no change. And you go down until you can generate the information, return results. You do that for all the different kinds of things. You return from impasses as you get information for them. And you ultimately end up with a choice of action. Turns out this corresponds fairly precisely to PsychSim's form of online reasoning. Okay, some quick comments on this. The automatic version requires 5 conditionals. This is the kind of distribution it gets, so it picks offering 1, and it requires 1 decisions with 94 messages. Controlled version, 19 conditionals. Here's the distribution. Again, it chooses 72 decisions, large number of messages, a large amount of time. Now, the distributions are essentially comparable, and it makes the same choice. But we get a speed ratio of about 6,000 between the two. So what we get is the same result with distinct computational processing. Automatic is fast, occurs in parallel with other processing. Controlled is slow, sequential, and so on. It also, in general, this distinction maps onto expert versus novice. This is kind of novice. This is expert. So it provides that aspect here as well. And it also raises the possibility of a generalization of a kind of learning mechanism that was in SOAR called chunking, which would automatically compile these trellises from problem solving. I'll get back to that shortly. Okay, conclusion. Simultaneous games solvable within a single decision, yielding Nash equilibria, except for when you're limiting yourself to the linear combination, in which case you can't always guarantee it. The sequential games are solvable in either automatic or controlled fashion, and it raises the possibility of a new form of structure learning in these kinds of graphs, which is a variant of chunking, which essentially learns probabilistic trellises, like hidden Markov models, dynamic Bayesian networks and so on, from more explicit cognitive problem solving. So that would be kind of interesting. It's one of the areas we're working on now. Required 2 modifications to sigma. We had to extend it from multi-agents, and we added this bit of exponentiation. And this is just where we're going. And that's it. Thank you.
Thank you, Paul. Do we have the next speaker in the room? We have time for maybe 2 questions. See if I can run without getting tripped over. Thank you. Have you looked at any kind of role of utility learning as well as the structure learning, the actual utility elicitation, combining?
Yes. So one of the things you showed last year at AGI was an approach to reinforcement learning in Sigma. And it was able to learn models of rewards. It was able to learn models of actions or transition functions, as well as learning reinforcements, doing the standard reinforcement learning of learning Q functions. So we actually were able to use a single learning mechanism to do all 3 of those forms of learning in terms of learning functions in factor nodes in the factor graphs. And at ICCM, we just did a piece that showed broader forms of learning, including simultaneous localization and mapping, supervised learning, unsupervised learning, again, all with a single learning mechanism.
Thanks.
So Paul, I think I've lost the top level view of this. So can you connect this to human level AGI? I mean, where's, other than a program for playing certain games?
So what I didn't show was the last thing, the slide showing the different kinds of things we've worked on. So this is an attempt to build a human level AGI architecture. And we've been able to show how we can do things like semantic, episodic, and procedural memories, all using the kinds of conditionals that I've shown here. Been able to show SOAR-like problem solving as well as POM-DP decision theoretic-like problem solving. We've been able to show perception, both elements of visual perception and speech recognition. As I mentioned, different kinds of learning, some aspects of natural language, all essentially using the same architecture by taking advantage of the generality provided by the factor graphs underneath the cognitive architecture. So it is an attempt to build a broad architecture from a very uniform base.
Great, thanks. I think we have to move on. The next speaker is Klaus Stranegård. Is that correct?
Yes, that's correct.
And the paper